Yeah, thank you so much, Horace, for the impactful talks. Welcome, everyone, to this lightning talk, making the most of heterogeneous memory capacity using PyTorch. My name is Syed, and I'm excited to represent our PyTorch core team at NVIDIA on this stage today. So thank you for giving me this spot. So for this next 10 minutes, I would like to talk to you about memory pools in PyTorch and how it can unlock some new CUDA features. This abstraction already exists in PyTorch and has been there for a long time. Under the hood, the CUDA caching allocator, it maintains several pools of memory, a large pool and a small pool. What we found was when integrating CUDA graphs, we needed to add one more feature. And that feature was CUDA graph needs persistent memory addresses. Between CUDA replays, it needs to remember those addresses. So one of the easiest ways to solve that was to OK, let's just create another new pool. And now all the CUDA graphs are going to be just putting their memories in that pool. We get to control the addresses in that pool, and our problem gets solved. So I want to convince you today that this abstraction lets us add even more features. So the feature that I want to talk to you about today is memory pools in PyTorch can enable usage of different CUDA allocators in the same program. So the way we want to do it, it's an API that's already proposed. There is some PRs already in. There is also an RFC on this issue. We want to lift up this abstraction, and we want to let you customize memory pools through this Torch CUDA MemPool API. So on the right-hand side, for instance, you can see that we are passing in a new system allocator. This system allocator is a nickel mem alloc, nickel mem free. And we're customizing a pool with that allocator. We pass that allocator into that pool, and we use a context manager to mark a region of PyTorch code saying that, OK, this tensor will get allocated with this custom nickel mem alloc system allocator. You can also see that the allocations before the context manager and the one after it, they're actually going through the normal default path of the PyTorch's allocator. This is an important aspect of this work because there is no one-size-fits-all allocator. Being able to mix and match different system allocators in the same PyTorch program would give you the most performance and memory savings in modern heterogeneous systems. So yeah, there is a stacked PR right now, and that is currently in active review. If you want to try it out right now, we have it experimentally released on our NVIDIA NGC Docker container, so you can pull that out. And I have some examples later in this talk. You can follow that example to see to play around with this API. So the rest of the talk, I want to talk about why do we need to use different allocators in the same PyTorch program. And this is, in my opinion, really because computer systems are evolving, which is very evident if you just compare system diagrams over the last few years. And they're really being driven by deep learning workloads. And the need to change certain parts of a system really arises when we are trying to accelerate these workloads. For instance, when we are running tensor parallel and we're trying to overlap a communication pipeline with a compute pipeline, sometimes you can see contention for GPU resources. So for specific tensor sharding cases, if your all reduces are very small, communication pipeline can steal resources from the GPU, and it can slow down your gems, for instance. There are also use cases, for instance, if you're trying to save your model for model checkpointing. If you try to all gather on the CPU, you can go through the network interface card path, and that has a reduced bandwidth versus if you were to go through like NV switch, for instance. Also in like DLRM workloads, if you're embedding tables, if they don't fit on the GPU, you might need to partition them to like the CPU as well. So a few years back, when we were able to buy GPUs and buy a CPU connected to our motherboards, this is what a multi-GPU system in my head looks like. Note that these diagrams are not really any real hardware products from NVIDIA. It's just my mental model of the current systems. We would run ResNet 50 with distributed data parallel, and then suddenly we would see that, OK, our all reduces in the distributed data parallel, which is the important communication up in that parallel regime. It would slow down because the interconnects being used are PCIe Express interconnects. So fast forward, these next generation systems, they're like, OK, we need to accelerate all gathers. Let's just put in some high bandwidth interconnects between the GPUs, which are the NVLinks. Let us put some high bandwidth interconnect between CPU and the GPU. One of those systems is server PCI Express module. And all of a sudden, your all reduces become faster. So we keep moving on, and just to drive this point a little bit more, great CPU-based systems, they're also changing the interconnect between the CPU and the GPU with an even faster interconnect called chip-to-chip interconnect. And to drive this point even more, if you connect multi-GPU systems into a multi-node cluster, you can now see that what really is happening here, the trend is we're trying to push the bottlenecks out, and systems are being iterated on. So for instance, in this diagram, multi-GPU systems are connected over into a multi-node system, and then we're connecting the CPU side with Bluefield data processing units, and then the GPU sides are connected with NV switches. So those are accelerating the communication between these multi-GPU systems. So now that you've seen how deep learning training app, it drives the physical blocks in our systems to evolve, my next point is evolving systems require programming models to evolve. And what I mean by that is when we change the interconnects, it brought in some new requirements. For instance, when communicating between GPUs through the NV switches, we might need the buffers to be of a certain alignment. Or if you're trying to access a buffer from one node to another in a multi-node system, you might need to ensure that the buffers are set up correctly for inter-process communication. And one programming model to abstract such requirements are through the use of system allocators, such as malloc or CUDA malloc, which you might be aware of. But not all system allocators are created equal, or there is no one-size-fits-all system allocator. What I mean by that is, for instance, if you create a memory with CUDA malloc, you won't be able to access that memory from the CPU, for instance. You will need to do a copy. Or let's say, for instance, if you want to access the memory of one node from another node, you will need to use the CUDA virtual memory management APIs, which are CUMEM, create, CUMEM address mapping style APIs. So we need to be able to accommodate such evolving programming models. And so evolving programming models require us to enhance PyTorch internals. And our goal here is to make PyTorch more expressive and more tunable for scientists, framework developers, and computer architects, tunable for everybody in the stack. And so we dive into PyTorch internals. We look into PyTorch's CUDA caching allocator. CUDA caching allocator is awesome and battle-tested. It has several features we care about, such as caching and fragmentation mitigation techniques, such as splitting, merging blocks, also using Zach DeVito's awesome expandable segments. However, it's challenging to add new functionality to it. And we cannot mix and match different CUDA system allocators, since this CUDA caching allocator is a global allocator. So by exposing this mempool abstraction to the user, we get all the benefits of the CUDA caching allocator plus some. We're able to mark a region of PyTorch code to use a different allocator. We're also able to use multiple memory pools, and so we are able to mix and match these system allocators. And so consequently, what happens is through this exercise, we unlock several features that can help improve the performance of your workload. And also making workload utilize more parts of your heterogeneous system. For instance, here is an example that shows an extended GPU memory based all gather. Extended GPU memory, or EGM, is a fancy way of accessing memory directly between GPUs that I'll get to in a second. Here in this code, you can see I'm using a custom allocator. I am allocating the output lists of the gather with that custom allocator, and then I just issue the gather, and then it uses EGM path. Diagrammatically, to explain this, if you are not using any of those changes, your gather is going to use the network interface card bandwidth, which in the figure I've shown about 100 gigabits per second. Whereas if you use the EGM path with all the mempool changes, you will be taking the NV switch path. So a second use case I want to elaborate on is the NVLS reduction. So these are NVLink Sharp reductions. So we allocate memory similarly using a custom allocator. We also allocate the reduction buffer using this custom allocator. There's only one extra thing we do here, which is registering this memory through nickel so that we can save on a copy. Also, it's known as zero copy. What happens with this code here is, without the changes in the MemPool API, with the MemPool API, when you overlap tensor parallel, when you overlap communication and compute, you actually sometimes steal resources from the GPU. By offloading these compute operations to the NV switch, you're able to give some of those resources back to other computations like gems. Also, you save on the copy because you're using zero copy buffers. So to summarize, I've shown you how you can use this API in your training. You can also imagine how we can integrate this API into training tools like tensor parallel, also like asynchronous checkpointing that we've been hearing about in this talk, in this conference, or even write a clever memory planning pass for deep learning compilers. So I just want to leave you with these takeaways. Computer systems are evolving. Evolving systems require programming models to evolve. Evolving programming models require us to enhance PyTorch internals. Memory pools in PyTorch enable usage of different CUDA allocators in the same program, unlocking several features such as EGM-based allgators and NVLS reductions. Thank you so much for listening, and thank you to the organizers and support crew for this wonderful conference. Thank you so much. I know we're late for lunch. Maybe I'll take one question, but I guess that's it.